All right, in this video, we're going to be taking a closer look at linear functions. We're going to look at some very specific characteristics that make functions linear, how we can identify them using average rate of change, and determining when linear functions are increasing, decreasing, or constant. In general, a linear function is going to be any function with a constant average rate of change. All right. In general, average rate of change, it's just looking at how quickly our x coordinates change in comparison to our y coordinates from point to point on any given curve, right? Well, for a line, that change is always constant, which means average rate of change for lines can be defined using our slope formula. The change of y divided by the change of x is nothing more than y sub 2 minus y sub 1 over x sub 2 minus x sub 1, given that those are 2 points on a line, okay? All right, so based on that, we want to know out of the two data sets here, which one is linear, okay? We can use average rate of change to determine that. In the first data set, we're comparing time with population of a bacteria colony. And you can see that we have several ordered pairs listed. From the first 2 points, I'll look at the average rate of change. Change in the y values is 0.03. Change in the x values is 1. So, of course, that average rate of change is 0.03. But then when you go from the second point to the third point, your average rate of change is now 0.04 over 1, or 0.04. Okay? The fact that the change of y divided by the change of x is not constant means that the data is not linear. Okay? Really, this data is exponential in nature, right? The growth of bacteria is said to be an exponential growth. All right, the second situation we have here is comparing age of a person and the maximum number of heartbeats, probably while they're exercising, okay, based on that little picture there. You can see for the first 2 points, the change in the y values is negative 2.5, and the change in the x values is 10. So that's going to divide out to be negative 0.25. Okay, and I think that's meaning that your heartbeat's going to decrease a quarter of a heartbeat for every year that you get older. From the second point to the third point, notice it's the same thing. Change of y's is negative 2.5, change of x's is 10. So we have that same average rate of change. And it would continue like this for the next several points. So since these are constant, we can say that the data is linear. Okay. All right, moving forward. So let's say we're looking at a linear function f of x equals mx plus b. Notice I'm using function notation here. We can say that that function is increasing as long as the slope of the line is positive. Okay. It would be decreasing if the slope is negative. And it would be a constant function if your slope is 0, where you have a horizontal line. Okay. So as an example, I have graphed over here f of x equals negative 5x plus 7. That line has a slope that is negative, which means the function is decreasing entirely on the interval from negative infinity to positive infinity. All right. Based off this, let's determine whether the functions below are all increasing, decreasing, or constant. S of t equals negative 2t plus 6. That's decreasing. It's got a negative slope. H of x equals 6. That would be a horizontal line when graphed, so it would be constant, where the slope is 0. And then m of n equals 6n. That's got a positive slope to it, so we are increasing. All right, so I don't even really need the graph of each of these in order to determine whether it's increasing, decreasing, or constant. I can focus solely on slope. All right, moving forward. Here we have two linear functions, f of x and g of x, and we have four different problems that have been posed. We want to find them all algebraically first, and then once we've found them algebraically, we're going to graph the two functions, and we're going to see how the graphs match the solutions for each one of these problems, okay? So the first problem or first question is, when is f of x equal to 0? Now, algebraically, I can just solve that essentially with substitution. F of x is equivalent to 2x plus 4. So I want to solve that for x. That would be when x is negative 2. Okay. Part B, when is g of x less than 0? Well, similarly, I can use substitution here. G of x can be replaced with negative 2x plus 2. So I'll subtract 2 over, divide by negative 2, flip the inequality symbol. That's when x is greater than 1. Part C, when is f of x equal to g of x? So basically that's saying for what x values are the y coordinates of f and g the same? So use substitution. F of x is the same as 2x plus 4. G of x is the same as negative 2x plus 2. Solve for x. I'll move my variables to the left, my constants to the right. X is equal to negative 1/2. Okay. And then when is f greater than g, meaning for what values of x are the y's in f greater than the y's in g? Use substitution. This is essentially going to be the same process as the previous problem in part C, except it's an inequality now rather than an equation. You'll end up with 4x is greater than negative 2, or x is greater than negative 1/2. All right. So now let's graph both of our functions as lines and see how our answers for these four problems relate to those graphs, okay? I'm going to graph f in red. It's got a y-intercept of 4, slope of 2. I'm going to fill up the graph with as many points as I can. And then I'll graph g of x. Let's do it in green. Y-intercept is 2. Slope is negative 2. So this time when I go up 2, I'm going to go left 1. Or if I go down 2, I'll go right 1. Okay. So question A was asking is, when is f of x equal to 0? And it resulted in an answer of x equals negative 2. Well, for that, we would solely be focusing on the red line here, okay? And saying that f of x equals 0 means you're looking for a point on the line for f of x whose y coordinate is 0. So even without knowing the equation for f, if you had the graph of the line, you would just be focusing on that point right there. It has an x coordinate of -2 to match 0, okay? For part B, g of x, when is it less than 0, okay? So basically we're trying to find all points on the line, the green line, g of x, whose y coordinates are negative, And that would be all of these points right here. We agree? If they're below the x-axis, then their y values are negative. Well, what our solution is representing, x greater than 1, it's representing all of the x coordinates of those points that I just drew over that are in blue. Okay. Part C, when is f of x equal to g of x? So again, we're saying for what value or values of x are f and g having the same y coordinate? Well, that would be at their intersection right here. And notice it matches the answer, the x coordinate of that intersection point is -1/2. Okay. And finally, D, when is f greater than g? Meaning for what values of x are the y's in f greater than the y's of g? Well, this is where I think the graphs are very helpful visually. So F is your red line, green is your g of x, right? And if I want the points of F to be having larger y values than the points of g, then that means I want the red line for F to be higher in comparison to the green line for g. So that would be right here. That would be all of these points on the red line. They are going to have larger y values in comparison to all of these points, right? So basically we're saying where this intersection point is taking place, anything to the right of that, so any values that are greater than an x value of -1/2 would match that criteria. Okay, so that's what the answer for D is representing.